Hi, welcome to this video. I'm going to talk about sugar stereochemistry and their most common structures with the help of the most famous one, which is glucose. I hope you like it. Stereochemistry in sugars. The easiest way to start is to use the monosaccharide glucose as an example. The most common is the cyclic structure and the chair is the best 3D representation. The molecule is easy to remember. All the hydroxides are in the equatorial position as well as the CH2OH substitute in carbon 5. At the first carbon it is beta glucose when the hydroxide is equatorial or alpha if it's axial. All carbohydrates have the same molecular formula. They are hydrated carbons. A disaccharide is formed by two monosaccharides. Lactose is a famous one. It is formed by two monosaccharides, glucose and galactose. Galactose differs from glucose in the stereochemistry of carbon 4, which is the axial position for galactose and in the equatorial position for glucose. Glucose and galactose are therefore stereoisomers. Beta-D-galactose and beta-D-glucose are shown here. They are diastereoisomers. Beta-D-glucose and alpha-D-glucose differ on the stereochemistry of the carbon in the first position, but they coexist when they are in solution because the hemiacetal bond is not a stable bond. The chain is opening and closing the whole time, making both stereoisomers possible. Here is shown how both alpha and beta coexist in solution. Mutarotation is the proof that both are present in solution, alpha and beta-D-glucose. The chair structure was easy. Now we can derive the Hayward structure from this. Also the open form of the chair structure, as a zigzag can be derived from the chair structure if we try to follow the molecule in 3D as it opens. The thick line here means that the molecule is pointing towards us. The most tricky projection is the Fisher projection. It looks simple, but it isn't. It can be derived from the Hayward projection by turning the molecule anticlockwise 90 degrees and placing the hydroxides and hydrogen substitutes to the left or right, respectively. The last substitute has to be turned anti-clockwise to reach the Fischer projection of glucose. With this projection, all the stereoisomers of glucose can be identified, as we have 4 chiral carbons. The D comes from the 5th position, hydroxide to the right, which is the same as the R, and there are 8 D sugars possible.